Yeah, so we are kind of getting on the edge of the technology to begin searching in infrared in this way. But infrared beams would have to be aimed directly at us. And this is good. It's good because then you don't have to waste a lot of energy that is spread out over a lot of volume where nobody's going to ever pick it up. The more tightly you can focus your beam, then the better the energy conserved in sending your signal. Okay, so this is good. They'd know that we're here. That part's easy to determine for them. We'll talk about that. Maybe the bad part is that if they don't want to let us know about them, they can avoid aiming their beams at us. I mean, maybe there's a galactic civilization out there and they're all talking to each other, but only after they've passed a certain test of being benevolent and friendly and treating their planet well. And in those regards, then, we don't pass. And so maybe they don't want us to know that we're out there. Okay, ET phone home. How many civilizations in the galaxy are there? So now we're going to do the Drake equation. Here's the original Drake equation. Now, initially, to ask the question, how many interstellar capable communicating civilizations are in the galaxy might seem to be a completely unanswerable question and suitable only for armchair speculation without much of anything in the way of input. But Frank Drake, way back in 1960, realized that, we could take that question and we could break it up into a series of just basic freshman probability. And that would then allow us to then make progress, perhaps, on each of the individual terms, rather than just leaving it all as one forbidding question that we don't know how to deal with. This is how to deal with it. So it was conceptually a great advance to just come up with the Drake equation, even though really it's kind of obvious if you just think about it. Here's the context in which you want to think about it. You imagine that there's life in the universe, but that that there are planets out there. Again, the environment has to be warm, not too cold, not too hot, so basically we're confined to planets. We need to have planets be the right temperature, as well as satisfying a bunch of other good things, as we'll see. And they're going to be life suitable and maybe even populated by an intelligent, advanced civilization, but not forever. There's going to be some lifetime associated with them. And so that's this. And so the way I try and have my students picture what we're talking about is imagine a dark, dark living room on Christmas Eve, and you walk in and all you see, well, you don't even really see your Christmas tree. What you see is a Christmas tree lights. And it's those little lights that they flash on, and they're on for a while, and then they're off, and then another light comes on. And that's kind of the way you want to think about the galaxy. There's civilizations that come and go. They come and go, come and go. Different stars, different planets. Maybe the same planet will have an intelligent civilization more than once. Who knows? But you can't assume that they are all starting civilization at the same starting gun. And you can't assume that once they get started, they last forever. So you then realize that, well, gee, the Earth was born at just some random time. We find ourselves now, finally, at the doorstep of being able to communicate in an interstellar way with other communicating civilizations. Happens to be 13 billion years after the galaxy was born. Not right after the galaxy was born, but 13 billion years. And 4.5 billion years after our star was born and our planet was born. So we don't know who's out there. And so the way to do it is to think of it as a random statistical probability distribution. So our stars, the rate of formation of suitable stars. How well, this is really a birth rate, is the way to think of it. And this is kind of a death rate. How long do they last before they die? And everything in between here is just a bunch of fractions. A fraction between 0 and 1 as to what are the odds that these situations will work out correctly. So this is a real physical number, and that's a real physical number. This is in years. This is in per year, stars per year that are born. And everything else in here is just a dimensionless fraction. So let's take a look at them. So we're going to find that some of these numbers we know reasonably well, most of them we don't know very well, and some we don't know anything at all about. So let's put some numbers to these terms. The rate of formation of suitable stars. So we need temperatures that are suitable for complex carbon molecules. So we need temperatures of roughly 300 Kelvin, somewhere in that general ballpark. And we need a liquid environment for chemistry to happen. Not too hot, breaks apart stuff. Not too cold, things find it hard to reproduce if you're frozen solid. Stars are too hot, we need planets around stars. Okay, so life, the only life that we know of, there's only one case that we know of a living planet, and it's ours. It took 4.6 billion years to evolve interstellar communicating life on our planet. Is that typical? Well, let's assume for the moment that it is. We've got a sample size of 1. I know that's hard to argue with, but it's all we got. We're going to take it. We may need most or all of that 4.6 billion years to evolve complex life. Now you might say, but Rick, you told us in the past in the other class that life got going on our planet early. We had life going back, 3.5 billion years ago at least, and maybe more. Yeah, but that life stayed as primitive single-celled ocean organisms. And it didn't actually turn into plants and animals until just 500 million years ago, so 500 million. So of this 4.6 billion years, we had only very simple life for the first 4 billion of it. Only during the last 0.6 billion, roughly, have we had complex life, something you might want to think of as complex. So again, it seems like it might take a long time. There are problems, okay? So to have a living planet, you don't want to get deluged with ultraviolet. Ultraviolet kills stuff. So you need oxygen or something else maybe that can absorb ultraviolet light. So on our planet, it looks like we didn't really develop a good oxygen atmosphere, a strong oxygen atmosphere that therefore had the capability of supporting high energy organisms like mammals, like us, or even fish for that matter. We didn't have that until pretty recently, like just maybe 500 million years. And we had no oxygen at all in the atmosphere, we think, for the first, 2.5 or 2, I guess, billion years. Little bit of oxygen after that, but not enough. And then only the great oxygenation led us to the possibility of energetic, complex life, because oxygen is such a great chemical for getting biological energy out of, but it's also a very toxic element if you don't take good care of it. I mean, too much of a good thing and you die. So again, is this timescale typical? We don't know. We're going to assume that it is. Useful clock to remember. If the entire history of the planet is 1 day, then complex life evolved only at 9 p.m. if midnight is right now. So if that's typical of other stars, we can tell you. Nice simple number. To get stars that are long-lived and stable, and they aren't too messy. They don't put out too much ultraviolet. They don't have flare stars, with toxic flares on them like M stars. But you want them to be long-lived. You want them to be reasonably cool, but maybe not too cool. You're talking about G and K main sequence stars. And we know the rate of formation of solar-type stars. It's about 1 per year. Well, what fraction of these stars have solar systems? Until recently, we had no idea. Now we know that nearly all stars have planets. So the Kepler mission and the earlier studies have demonstrated that to us. And we also know, more focused, more important, about 20% of the solar-type stars have small planets relatively close to their parent star. So that fraction looks like 0.2. So we got our first term and our second term in the Drake equation. Okay, so how many life-suitable planets are there per solar system? Number of life-suitable planets per solar system. This is a more intricate question than could be dealt with back in Drake's heyday. Although Frank Drake's still around, he still shows up at the university. He's up on the hill, UCSC, still doing very well. But he's one of our heroes. Okay, what do I want to say next? Okay, in our solar system we have maybe 2 planets in the habitable zone. Us and Mars. But Mars didn't work out. And Mars is dead, and it never developed, well, we don't know. It may have never developed any life at all. But if it ever did develop life, it didn't last. Okay, so let's just say NP is 1. We got 1 living planet in our solar system, and we think that's reasonable. Okay, now what about the fraction of these planets? So now we have a planet that is in the habitable zone, and it's around a star that's suitable. So now we want to know what fraction of these planets actually have life. So just because it might be life suitable, what are the odds that it really does have life? So here the argument is that life is very tenacious. Bacteria and microbes seem to have invaded every corner of the earth. We find life inside of rocks, miles below ground. We see life at the bottom of the ocean where there's no light from the sun at all, and the whole energy mechanism has to be based on something other than photosynthesis. And yet there's thriving ecosystems down there, at least in some places. So it seems that if life is possible, it happens. And quickly. Again, we see life, irrefutable evidence of life on our planet 3.5 billion years ago, most of the way back to the beginning, and more contentious evidence for life, carbon isotope ratio, proper carbon inside zircons, and that argues that, well, maybe there is organic life, organically processed carbon isotope ratios. Yeah, it's pretty tenuous, but anyway. At least we can tell you that life on our planet goes back a long time. If life can happen, it will happen. That's going to be our assumption. Well, fraction of living planets with intelligent life. Okay, so this one is now we're getting towards tougher questions to answer. The key question to answer is, what's the survival value of intelligence? That'll tell you something about how often it arises. And you could argue both ways. You could say, well, initially intelligence seems to be pretty valuable. I mean, look at what we've done with our planet. We've become the dominant life form on our planet. But then somebody else with a little bit more future mind to them can realize, yeah, we're too smart for our own good. We've developed a technology to kill the planet, and it seems like we're over eager to use it. and are using it. From nuclear bombs to plastics to you name it. Now you could also argue that, well, but that's really just the economic system we evolved, isn't it? I mean, what if we had a different economic system based on a reward system that was a little more life friendly and not just so dog eat dog, devil take the hindmost, I'm taking my chunk of flesh first and the rest of you can, that's kind of the system we have. But is it necessarily what intelligence will evolve? I'm not sure. Not sure anybody is. And even at that, I don't think that no matter what kind of trials we go through during our adolescence as a intelligent species, I don't think we're going to go extinct. We are poisoning the planet, and we may poison it worse, and I think it is quite possible that we may have a collapse of civilization this century. And if not this century, early the next century. I think that is possible. But I don't think we're going to kill every last person on the planet. I think we will survive, and we'll learn, but we'll probably follow Nolthenius' first law, and that is, people learn the hard way. Okay, but we'll come back to stuff like that later. So, I think intelligence is probably gonna evolve at some point. It has been so serviceable in winning the evolutionary battles that I think sooner or later living planets, for the most part, are going to develop intelligence. So if you have a living planet, sooner or later you're going to develop high intelligence. Intelligence capable of communicating with other planets around other stars. Remember, that's what we define by intelligence. Now, how long it'll last is another question, okay? So we are, right now, an interstellar capable communicating civilization. Now, will we evolve back into, the world of Mad Max or, the Book of Eli or something like that? Maybe. But at least for the moment, we're still in the running. Okay, now here's another question that's more psychological. What's the fraction of intelligent living planets which choose to develop and use the technology to communicate across the stars? So you might think that, well, gee, if they can, of course they will. And that's not so obvious. Nature gave us motivational systems for us to be rewarded for pursuing the activities that would help us to propagate. That's natural selection. And one of those is a kind of generic curiosity. We want to know things. We are curious. We're a curious species. It's conceivable, at least, that another planet might solve that problem of getting their organisms that are going to be intelligent to propagate accurately and prolifically without engaging curiosity. And maybe they have no category even for the notion of why would we want to talk to other stars? It's like, why? I don't get it. I can't understand what you're talking about. Curiosity? I don't even know what that word means. That might be what they say. We don't know. By the way, gang, so it is now an hour into my talk, and yeah, we're still going, but you know what? This is such a great talk, I'm going to keep going. So I hope you stay with me. I can't imagine mature intelligence which is not curious. Just because I can't imagine it doesn't mean that it isn't quite possible. I will tell you also that the numbers I'm putting into the Drake equation now on this first go-through are numbers that were the common numbers for many years after Frank Drake initially published this. And frankly, they're numbers that, they're in service of optimism, and they're in service of helping to motivate us to put some money into the SETI project and go out and look. For sure, we're not going to talk to anybody if we don't try. Okay? But we can at least make some arguments here which are maybe a little optimistic, but they're reasonable. They're not obviously wrong. Just in case you're wondering why all of these probabilities turn out to be the maximum possible. If it can happen, it will happen. So I know I do get from students, and frankly I hear myself talking to myself in the same way. Are we too pathetic and ridiculous and corrupt to be curious about? And I just have to say, hey, wait, our species has produced more than just Donald Trumps. It's also produced Einstein and Rembrandt and Michelangelo and Da Vinci and Rachmaninoff and plenty of incredible, incredible people. And if not plenty, at least quite a number, enough to make a big difference in the culture of our species. So that's one argument. But the other argument is, we have curious scientists who they're fascinated with bloodworts and slime molds and doggy fleas. Wouldn't aliens therefore want to study us? I mean, if for no other reason than to find out where we went wrong? I think so. So I'm going to assign, as many others in the past, that if you can interstellar communicate, you will. Okay, now we get to the hardest term, the average lifetime of a communicating civilization. We have no idea, okay? The only living planet we know of is ours, and our L has not yet been defined. It's begun, but it hasn't ended yet. I wonder whether it might this century, thanks to climate change and, God knows what else. It might come out of biohazard labs and all that. Plasticizers, reducing our ability to reproduce, things like that. We really don't have any data on this answer.